Okay, so again, next a week from today we'll have the midterm. So our midterm is the next Thursday, 22nd October, and again, so you can have one sheet of paper with notes, both sides, normal size paper, like that. And on Tuesday, we'll go over last year's midterm. Last year's midterm should be up on the web page, so you can have a look at that and kind of get a feeling for what things will be like on Thursday. Okay, so I'd like to today continue our discussion on coherence. Again, this is a very important physical property of light that is sort of needs to be controlled for holography. You can actually so you can have sources again that have a what's called temporal coherence. So in temporal coherence, what we're doing is kind of comparing the phase difference that might exist at two different points, say P1 and P2, and so we compare them, and these points are separated either in length, that we can call a coherence length, or time, that are of course related by the speed of light. So, so we have temporal coherence, and we also have a spatial coherence, where if we have a source, may have some extent to it. Generally, we need an extended source for looking at the loss of coherence. And then we would sample here 2 points across the wavefront, spatially separated. So these are two really distinct things, are quantities, entities, with regard to coherence. Now, if we have a perfectly coherent source, that would be a point source that emits a single frequency of illumination or single frequency electromagnetic wave for all time. All right, so that, when we deviate from that, and also if we have a point source, then we also have high spatial coherence as well, right? Because there's no ambiguity, say, from light coming from these sections of this or points on that extended source. So a point source is really a good source to have for getting very high coherence. Unfortunately, no sources are really true point sources. They're pretty good approximations, but not quite. Now, there are times in holography actually when you don't want very high coherence, all right? And for systems that do kind of gating operations, we'll talk a little bit about this later in the course, but if you had a field that propagates, and so if we set up a little interferometer here, let's see if I could. So if we set up kind of an interferometer like so, and we have a some object in this path here, if in fact we kind of control the coherence, we could actually say make a recording of different, let's make that a little bigger, different planes inside that hologram. So by, again, and the reason we can do that is because we would form fringes when the path lengths actually match, right? But let's say we move this, so we have this on like a positioner of some sort, or a piezoelectric that can vary it, or there's a technique in medical imaging called optical coherence tomography, which kind of works on this principle, where you use an LED, which has a broad spectral bandwidth, and then you use fibers, which you can couple to this LED, and you make a fiber interferometer, and you actually change the path length using a kind of a mirror. So the light, will hit this mirror and then bounce back, but in the meantime it's moving. So you get a change in the exact optical path length in your interferometer, and by doing that, when the light is coincident, you get a very strong interference effect, or a stronger interference effect than the background. So you can do this, and that gives you a higher signal, and then you can also sync that with a lock-in amplifier, so you're only looking at light coming back at a specific frequency, and that will give you a way of subduing the background level in the image that you're trying to look at. And you can do the same thing in holography, and we'll talk a little bit more about the specifics, where you change the coherence length, but instead of using the fringe in this manner that's used in the coherence tomography, what you do in this case is that you change the position in which, in the object, that you'll get a fringe being recorded. So you can actually do kind of like a depth sectioning by changing that optical path length. Okay, so so understanding coherence is very useful. Okay, you can certainly, for most of the cases that you'll be looking at in holography, you're going to want to have a long coherence length, so you don't have to worry about path length differences too much. But there will be times when you can use that as a tool in designing a system that suppresses, in many cases, you can suppress background levels out of the image that you're forming. So again, keep that in mind when you're doing your work. So at any rate, we're kind of establishing some notions here about this coherence length and coherence time. And so we looked at a couple of examples. One, if we had two different frequencies, nu1 and nu2, with a delta nu, which is pretty small, say it's less than nu1 or nu2. In that case, we saw that we had a kind of a coherence length that kind of varied as a sinc squared function. And then also, if we had a time-varying phase between our two fields that we're monitoring, that would also give us a reduction in the coherence length. So again, what we're really doing is, at this point, P1 and P2, we're looking at the field here. So we have V at P1, and we have V, make it a complex term, V at P2, and we're comparing the fields at these 2 points. And in comparing the fields, what we're really doing is looking at the phase difference, the phase difference between the oscillations in those two fields. When that phase is a constant for some distance LC, then we can say that we have a coherence length that is LC long. All right, so that's what we mean by the coherence length, and that's what we mean by this notion of coherence, is that we're actually sampling the field at two different points, either along the direction of propagation or across the direction of propagation. So let's continue to look at this in the sense of considering different types of field emissions from a source. All right, so now we started looking at this last time. So let's look at a pulse of monochromatic light. All right, so we have a field which emits a single frequency or single wavelength light. And if if this were a truly monochromatic field, then the spectrum that we would have for that would be simply a delta function. All right, so the kind of the Fourier transform relationship between this time-varying monochromatic field and its frequency spectrum is simply a delta function. All right. So now, though, we're going to take this and basically we're going to chop it. All right. So we're going to, the field kind of starts and stops at some point. So this could be the result of, say, in Doppler broadening of a gas that's emitting. So you have atoms that are emitting at a single frequency that you've excited, but then they, collide with one another, and you end up disrupting that phase. All right. So the phase may now shift to maybe another point, and it starts oscillating this way. All right. So we could have a pulse of light in that manner as well. All right. So our description for the field now that we're examining is equal to a e to the j 2 pi nu 0 t. And so this is for a period of time, delta t. So t, let's say, is less than or equal to delta t over 2 and greater than or equal to minus delta t over 2. All right. And it's going to be 0 elsewhere. So for times less than minus delta t over 2 and greater than delta t over 2. All right, so we have this, this pulse. So this is our c delta t now. The length of this pulse is going to be that long. And so now let's look, what we want to do is figure out what the frequency spectrum is. Because already, from just considering this monochromatic field, we kind of know that the monochromatic field has basically an infinite coherence length. For a monochromatic field. So that's kind of our reference point. And so again, that's represented here by this single delta function frequency spectrum for the monochromatic field. All right. So we already see that we have a Fourier transform relationships there. And again, so this is the spectrum of our field. So let's look at the spectrum of this field that we just constructed here, this pulse. All right. So we have now the field, the Fourier transform of that time-varying field, v of nu. Here, this is going to be, again, since it only exists for these time durations, our infinite integration is reduced to minus delta t over 2 to delta t over 2 of e to the j nu 0 2 pi t, and then e to the minus j 2 pi nu t dt. All right, so this is just we can combine this as a constant frequency here, so we can combine that into here. And if we look at that, this is just a kind of a rectangular function, right? So we're taking the Fourier transform of a rectangular function. We're going to end up with a sinc function. So it's exactly what we get. So this is just equal to delta t times sine of pi nu minus nu 0 times delta t divided by pi nu minus nu 0 delta t. So in order to get it to sinc, I had to multiply by delta t top and bottom there in order to make that, that work. And again, that should not be too surprising, since this is essentially a rect function. It's on with a single frequency, and then it's off. Okay. So and we have this notion again too, that somehow the frequency spectrum that we have is related back to the coherence length. And more specifically, the coherence length is related to the power spectral density. for a source. All right, so again, these are all source parameters. And the power spectral density is just this spectrum of this field times its complex conjugate. So we have V of nu complex conjugate times itself, or times the unconjugated value, gives us this magnitude squared. And so we end up with a delta t squared, which really is not that important for our cases here, sine of pi times nu minus nu 0 delta t over pi nu minus nu 0 delta t squared. So the power spectral density is a sinc squared function, all right, and so we end up with, again, our sinc squared function that we looked at earlier from diffraction analysis. And so the width of this is going to be related, again, this Fourier transform notion with the coherence length comes about because the width of this spectrum, however we measure that, delta nu, is going to be related to the coherence time, all right? And that coherence time, again, is the distance between those points that we're comparing in the propagation of this field. So this is the coherence time, and then we can get a LC coherence length, so let's call it TC, or tau C is just C times tau sub C. All right, so this is the notion that we have. So one question that comes up, though, what is the actual value that we would have here for the width? So if we take this to the first nulls that we have, this is then going to be when nu minus nu 0 is equal to 1 over this time interval, this kind of sampling time interval that we had between those two pulses. All right, so we have a kind of that value on this side and a null on that side. So if we take this as our delta nu, all right, then that's going to be, our delta nu then is just equal to 2 over delta t, and so we can say that's equal to our coherence time, all right? Now notice, the broader, actually, this, the broader that this spectrum is, the shorter the coherence time is, okay? So, and it turns out that a better measure, actually, for the spectral width is the full width half maximum. So if this is normalized so that that would be 1, then this has a value of 0.5. And so now, if we were to obtain that value, which I think I asked you to do actually in homework 4 on one of the problems, we would just take this sine, look at sine of pi x over pi x squared, and we set that equal to 0.5. And this occurs when x is about equal to 0.44. So if you put 0.44 here into x, this function works out to be about half. And now we have, but that's only, for 1/2 here. So we end up with a nu 1/2, so we would have nu sub 1/2 minus nu 0, the center frequency, of course, is nu 0. This then times delta t is equal to 0.44. But what we actually want is the full width at half maximum, right? So we have to multiply that by 2, all right? So we end up with delta nu is equal to 0.88 over delta t, all right? So again, so this then gives us a kind of a value for our coherence time, because now the coherence time is going to be just delta t over 0.88. All right. And the length L coherence is about 1.136 delta t times c. All right. So again, so this is kind of a way in which to evaluate the coherence of a different source. So again, this would be some finite pulse width for this source that's emitted from an optical source. All right. So all right. So we've been kind of vague about this coherence length and coherence time. We said it's kind of related, as we said, to we have this notion here of the coherence time being inversely related to the spectral bandwidth or the bandwidth of our power spectral density. But let's, there's a more formal way of defining this. All right. So the formal way of defining it is through the degree of coherence function. And sometimes it's called the complex degree of coherence function because it actually is a complex number. And again, it all relates back to this idea that we have this wave, and again, this is related to the temporal coherence, by the way, which turns out to be a little more significant for a lot of our purposes in holography than the spatial coherence, but nonetheless, you do have to pay attention to the spatial coherence. But again, this definition is based on sampling these two fields. So again, we have V at P1 and V at P2. We compare those two, and we're over some period of time, and we look to see how that phase what that phase looks like. Does it change with time? Does it stay the same, or is it constant? If it's constant, we have good coherence over that path difference. And we monitor this by, again, looking at, what we would do here is put this in a interferometer and measure the visibility of our fringes, where we would have Imax minus Imin over Imax plus Imin. Okay, so the actual operation that we're doing is we're taking this V at, say, P1, that might be at time t plus tau, where tau, again, is the coherence time related to the separation of those 2 points that we have, times VP2 measured over here. All right. So we have to look at this over some period of time. And for instance, in our case, one of the time periods we'd be interested in is, say, the exposure time of the film that we need to have this good coherence for. All right. So if we take this, so this is fundamental to having a representation of coherence. And so the complex degree of coherence function is simply the normalized version of this. So what we do then is just divide this by Vp1 of t times Vp1 star of t, which is just the intensity for that first field, and that times the Vp2 t Vp2 star of t, also time average. And so that's equal to I2. All right, and so what we have then is we have this time average of V1, V2 star normalized with the intensities. And this is often referred to as, again, this complex degree of coherence that has a parameter in it, tau, which represents the coherence time for those 2 sampling points. All right. So that's the function. And if we now simply, so let's remember something else that we talked about a few times in class. And so if we have a interference measuring this visibility, we know also that we have, say, the intensity for those two interfering terms is going to be equal to I1 plus I2 plus, we have 2 times I1, I2 cosine of the difference, but that cosine term we can also represent simply as 2 times the real part of this time average of V1 tilde V2 star, right? That's really what that interference term is. It's, again, the correlation of those two fields that are overlapping and producing the fringe that we're measuring. All right? Okay, so getting back to our equation that we have, so we have to evaluate this. All right, so that's not too hard. All right, so we have our gamma 1, 2 of tau. This is equal to, say, the limit as t goes to infinity of 1 over 2t integral minus t to t of v p1 of t plus tau, vp 2 star of t dt, and that again is over I1 plus I2. Oh, and I forgot, there should be a square root because we want to have that as a, this is going to be an intensity normalized to a single intensity. So, so we have not I1 plus I2, I1 times I2 and that to the square root. Okay, so all right, so we have this this term that looks like this, and so we can say now that we have VP1, VP2 star, the time average is just, this term here is just equal to this complex degree of coherence function times this product of the intensities. So we have I1, I2 square root times gamma 1, 2 of tau. All right, and it's a complex function, so we could put a squiggle over the top to make it a complex number. All right, so, and we know, all right, in relating this to our fringes, that what we want is this term. All right, so what we need to do is take the real part of this, multiply it by 2. All right, so we'd have 2 times the real part of V1, V2 star equals 2 I1, I2 to the 1/2. That's already real. And then we have the real part of gamma 1, 2 of tau. All right. So if we have a real number, we can also say this is 2 I1, I2 to the 1/2 times we have a magnitude and a phase with a specific real value. So we can write that as gamma 1, 2.
What is gamma 1, 2?
That is, again, this function. That's our definition of the sampled points in this propagating field, at 2 different times or at 2 different positions, which corresponds to a different time, normalized to the intensity of the field at each of those locations. This is the definition of the complex degree of coherence function. Okay, and that's for...
Oh, I'm sorry.
What?
Notationally, is there any reason you're adding the tilde?
Yeah, because that's, if we want to say it's complex. Okay. Because in general, it will be a complex number. These are all complex here and here and here and here. All right. So here, if we're just taking the product of 2 complex numbers, we're going to end up with a complex number. So we can still have that. Yeah.
Also, notationally, is that actually V or is it like a Greek letter? Is it just a normal V?
Is it a V?
Yeah.
Yeah, that's a V. I'm sorry. So there's a lot of, please ask me. So that's a V. This is a nu, like that. So I'm trying to make my nus without that little arm there, that broken.
You were saying V, so I figured
Yeah, okay. Yeah, please ask me. I know I have terrible handwriting. That's why I'm trying to word process all this. It's coming. So anyway, stop me if anything is unclear. I'm more than happy to bring that up. So our complex degree of coherence function now is a real part and a phase part, also real, corresponding to that complex field. All right. So we have this now as basically, again, we have this term that appears in our fringe formula related to this kind of abstract complex degree of coherence function, which is really not that abstract, right? It's just the time average of our two sample fields. That's what the notion of coherence is. We're, again, averaging these two fields at two different points in space. So how are these related to something yet a little more concrete? Well, remember we have this V, the visibility. V is I max minus I min over I max plus I min. All right? So what is the maximum and minimum value of I? All right? Well, it's when this term here is either equal to, it's going to be maximum when this term is plus 1 and minimum when that term is minus 1, right? So we have I max is going to be equal to I1 plus I2 plus 2 I1 I2 to the 1/2 times this gamma 1, 2 is what we end up with the, so in this case, we have cosine of beta 1, 2 is equal to 1, and I min is, we're going to have a minus here, and that's going to occur when cosine of beta 1, 2 equals to minus 1. Beta equals, say, 180. Okay, so let's now...
And it looks like you dropped the tau. Is tau just showing that beta is some time dependent?
Yeah, I just dropped it. I'm sorry. We
That's
can
fine.
put it back in there, but it's in there. Okay.
I'm just making sure that's the function notation rather than a product.
Let's put it in there just to be consistent. Yeah, I just for some reason dropped it there, but yeah. So all of this again, tau is really important. Tau is telling us the sampling distance between our 2 points that we're using to measure this coherence length. All right. So now let's put this into our visibility and see what we get. So the visibility now is I max minus I min, so that's equal, these I1 and I2s drop out, and we end up with 4 times I1 I2 to the 1/2, and I'll be careful, gamma 1, 2 of tau magnitude, and I max plus I min, since this is a minus sign, this interference term now drops out, or the gamma term drops out, and we're left with 2 I1 plus I2. All right, so visibility is something that we're very familiar with, right? This is visibility. I know we have a lot of V's and news and all kinds of things running around, but that's the actual fringe visibility that we would see when we interfere two beams, like at our holography plate. All right, and now let's rearrange this a little bit. Of course, we can divide by 2 and do some other things. So we have 2 gamma 1, 2 of tau. And let's divide by this factor here. So we end up with I1 over I2 to the 1/2 plus I2 over I1 to the 1/2. And notice that if I1 equals I2, then V is equal to this magnitude of our gamma 1, 2 of tau, exactly. So this very physical experimental term that we're very familiar with, right? So this is telling us, we have fringes look like that. That fringe is actually, according to our definitions, the same thing as this complex degree of coherence function, the magnitude. But that's usually the term that we're interested in, okay? So again, it's not such an esoteric thing after all, okay? Now, one other thing as well. Let's go back. Let's look at this definition that we have for the complex degree of coherence, and let's make it a little more. Let's even make it more sound in the sense of relating it to the source spectrum. All right. So if we have again our gamma 1 2 of tau, put the tilde over it. And we have V of t plus tau, V star of t. We have the time average of that. This divided by, say, I1 plus I1, I'm sorry, I1 I2 times I2. All right. So, what?
Is there the square root in that?
And the square root, yeah, I'm sorry. Thank you. All right, so now let's just look at this top part again from a different perspective. If we look at that, remember we wrote it as this is equal to the limit as we can write this as the limit as t goes to infinity for our averaging that we have, times 1 over 2t, integral from minus t to t of v of t plus tau v star of t dt. All right. So what does that look like?
Gamma 1 2 times the square root of the irradiances.
Well, it kind of, it almost looks like we're a convolution, right? So if we take this, if we take these limits to infinity, then we have a convolution of these two, right? So if we were to take the Fourier transform of V1, V2 star, okay, which is, one has the tau in it and the other doesn't, right? Then we can write this really as being V1 of nu times V of nu, and we have an additive term here in that convolution. That additive term, this should be a star here, is going to give us a phase shift, e to the j 2 pi nu tau. Yeah.
Isn't it with the convolution that you have one term that's like a tau minus t, so that your integrations are actually rolling across each other?
Okay, so let's move it around.
Okay.
The main thing is it's a displacement of the, so it's just shifting it in the opposite direction, but for our purpose here, it shouldn't affect the result, in any significant way.
Okay.
Okay. So let's define this. So what is this? This is, we talked about this before, right? This is just equal to V of nu squared, and this is the power spectral density. So before we were a little bit, we're just sort of approximating this notion that this power spectral density is somehow related to the coherence length, but now we see that it's actually directly incorporated into our definition of coherence, right? And so here we have that this Fourier transform is going to be equal to this phi of nu times e to the j 2 pi nu tau. And we have to normalize it. So we could just say this is a normalized function and come up with our definition now for gamma 1 2 of tau is just equal to the integral minus infinity to infinity of phi of nu e to the minus j 2 pi, oh, I'm sorry, that's a plus there, j 2 pi nu tau. And this is integrated over d nu. Okay. And with the notion that the integral here, phi of nu, the integration of that, d nu, is equal to 1. So it's normalized, which is kind of what we have up here as well. Okay, so all these kind of different definitions you may have encountered, I've encountered several, are really talking about all the same thing, okay, in a different way. And the real key here is just that we're looking at these 2 points in space and comparing them. And the farther we can go apart and still get the phase to be a constant, I know I'm using phase that for the power spectral density, so the phase equals a constant, then the more coherent that source is. If we had, and in the extreme where we had a delta function, single frequency for all time, then we would have then infinite coherence length. Okay, so now there's several kind of typical sources that you'll encounter. For instance, looking at, in the lab we have a gas laser, right? So a gas laser, the spectrum that you have for that gas laser is typical. It's going to be Gaussian, have a Gaussian broadening, and that's due to this collisional effect, or I'm sorry, not the collisional effect, but to the fact that you have your atoms moving in different directions, and even though they're emitting at the same frequency, say nu 0, there's a different velocity component of them either moving towards you or away from you. And that different velocity component, just like the train going away from you has a lower pitch than when it comes towards you, you get the same sort of effect in optics. And so you get this Doppler frequency broadening. Which gives rise to a Gaussian spectral power density function. And so for the Gaussian, call that our source 1 here, we have a power spectral density phi of nu that's equal to 2 times the square root of ln of 2, there's just some constants out here, divided by pi, and also divided by this is the full width half maximum frequency width for that Gaussian, times the functional form, the exponential of minus 2 square root of ln 2, all that's under the radical, times nu minus nu 0 over delta nu and squared. All right, so that's a Gaussian function. You'll encounter that a lot with gas lasers, in particular argon lasers, krypton lasers, various lasers of that type. Okay, now there's another type of broadening, also occurs with high pressure gas lasers, which has a Lorentzian distribution, and this is again due to collisional broadening. And so what we mean by collisional broadening is, the atoms may be moving along here, of course, and they collide, right? No big deal there. But what happens to the fields that are emitted is the field may be emitted like a monochromatic wave, and then all of a sudden it shifts after some period of time, the collisional lifetime, and there's, say, a phase difference. So you end up getting lots of kind of pulses of monochromatic waves that are truncated, just like we did earlier in that analysis of a pulse emission. All right, and so the Gaussian distribution is somewhat similar to a Gaussian, but it has broader tails associated. I'll show you a figure of this in a minute. And this is kind of, again, function of nu. And this looks like 2 pi times delta nu. Actually, this is a minus 1 there times 1 plus 2 nu minus nu, say the average frequency over, I guess I should call that an average frequency as well, to be consistent, nu minus nu bar over delta nu, where that term is squared. So in a Lorentzian, you usually have kind of this resonance kind of characteristic where, you know, you see this in the denominator. And, you know, we could also kind of model, although it doesn't really occur in nature that much, or if at all, we can just have kind of a rectangular spectrum. And so we have, basically what we're saying is that we have, this is the frequency, so we have, you know, kind of constant emission over a band of wave frequencies. This is our nu bar definition, is the center of that, and then 0 elsewhere. So that, naturally, that's going to have some sort of sinc function or sinc squared function as the Fourier transform of that. So this is 1 over delta nu rect of nu minus nu bar over delta nu. So this is kind of a really more of a theoretical frequency spectrum. Okay. Now, notice that we have our definition. So what we want to end up with is the coherence time for these different types of sources. All right. So we need to, so we know we can get that coherence time from this complex degree of coherence function. And so what we need to do is that operation, right? So what we have to do is our gamma 1, 2 of tau is this kind of integration of phi of nu e to the minus j 2 pi nu tau d tau. I'm sorry, d nu. Okay, which is basically a Fourier transform. All right. All right. So now the if we go ahead and apply that to these different functions that we have, so we have gamma 1, 2 of tau for the Gaussian source spectrum. So this is going to give us one function out in front, exponential of minus pi delta nu tau divided by 2 square root of ln 2 times the exponential of minus j 2 pi nu bar tau. So what we end up with is a product of two functions. This one is an envelope function, and this one, as you can see here, is an oscillating function. So this is a fringe function. Okay. All right. So I'm seeing one slight inconsistency here, which may go back to your question about the convolution. And I was actually I kind of rewrote these notes this afternoon before class. So I'm looking here. So if we had this as t minus tau, okay, I think this is where the discrepancy comes, because nobody brought this up, but this should be a minus, right, if we want our Fourier transform. So the way we can get that a minus is if that shift that we were using in our convolution is t minus tau. All right. Again, I don't think there's anything technically wrong with that. I'm just going to have to clean up my notation a little bit throughout. But at any rate, we end up with this functional relation between the power spectral density and the complex degree of coherence, which is just a Fourier transform relation. Is that okay with everyone? Did you see what I just mentioned there? I noticed that I had this was a positive here, but the reason it's positive is because of the way I was taking the sampling difference in time. So I'm going to have to go through and change the notes so that we have t minus tau instead of t plus tau. But it's not a serious. It's not technically wrong, but it's a little inconsistent. So I apologize for that. So let's get back to the important thing here now. Looking at these degree of coherence functions for these different sources. So for the Gaussian source, we have this envelope function, which again, the varying parameter here is the spectral width times tau, and we have a fringe function in there as well. For the Lorentzian, bless you, we have gamma 1, 2 of tau, and again we have this envelope function, different envelope function this time, exponential of minus pi delta nu and magnitude of tau times, again, exponential of minus j 2 pi nu bar tau, so the same kind of oscillation. And then for the rectangular, no surprise, we end up with a sinc function, gamma 1, 2 of tau for the envelope. So we have a sinc of delta nu tau times exponential of minus j 2 pi nu bar tau. All right. So again, all of these have the form. So in general, we end up with a gamma 1, 2 of tau, which is equal to some type of envelope function times a fringe function, which is e to the minus j 2 pi average frequency tau. All right, so if we look at some of these functions, the form, so here again is our Gaussian that we started with, so we have that. These are kind of normalized in a sense. The power spectral density is normalized, so the area under the curves are all the same in these, okay? So, and then this is the Lorentzian, so notice we have these broader tails out here, and here's the rectangular function, all again with the same area. If we look at this gamma function that we have for the complex degree of coherence, we see, again, the Lorentzian is kind of a decaying exponential almost here, which exactly that's what we have, decaying exponential. We have Gaussian, which is a little broader, and the rectangular, which is this oscillating function like that. And again, so what you would see if you were to measure the source with your interferometer, you would see this nice envelope function, and then you would have these oscillations with that e to the minus j 2 pi average nu 2 times tau rather for that oscillating period. So there's one more step. Yeah.
Really quick, in that power spectrum, why do we get the mirror of the envelope? So you get the normal carrier on top, and then you get the mirror on the bottom to make that a full.
If you just look at the amplitude.
Well, so these are not squared. So for instance, your sinc function is, I guess that's the range of, it would be limited in both directions, right? So I think you just need to think of it in that way. like there's a, um, yeah, I guess,
It's just the amplitude of the function that has to
yeah,
follow
it's just the
line.
amplitude of the function, so, depends how you define it, I guess. All right. Yeah, so I guess I'll think about that, but yeah, it's maybe when you do the measurement, like you're measuring the intensity of that distribution, and there's some average value, and it just oscillates around the average value. So it's not. It doesn't say that this is negative here, right? So there's an average value, and it's kind of oscillating about that. Okay. All right. So the one thing that the final thing that we want to get from this is what is the the corresponding coherence time. For this, and so the coherence time is equal to the integral of this complex degree of coherence function, right? So if we have, again, this gamma 1, 2 of tau times its complex conjugate, integrating that over infinite time, that gives us the coherence time, all right? And so for the Gaussian source, we have a tau sub c, which is equal to, again, this square root of 2 ln 2 divided by pi times 1 over delta nu, which is 0.644 over delta nu. For the Lorentzian, the tau c for that is 1 over pi delta nu, which is equal to 0.318 over delta nu. And for the rectangular function, the tau c is just 1 over delta nu. All right? So our original thought about the coherence time just being related to the inverse of this frequency spectrum of the source was pretty good, right? It's modified, like, so the Lorentzian is the broadest of those sources. And so we see here that those very broad tails really diminish the, or reduce the coherence length or coherence time for that particular source. Notice, so that one has a 0.318 for the value for that multiplier times 1 over delta nu. So just quickly, if we look at an actual source, some source values here. So let's say that we have a delta lambda of 20 nanometers, and we have the lambda average here is 850 nanometers. So what are the coherence times for these? If we had a Gaussian, Lorentzian, and a rectangular function with a bandwidth corresponding to delta lambda of 20 nanometers, what would be the coherence time? All right. So first thing you have to do is convert the spectral bandwidth in terms of wavelengths into frequency. All right, so we know that nu is equal to c over lambda, so delta nu is equal to c over lambda squared. Delta lambda, there's a negative sign in there, but it doesn't really matter in this case. And so this frequency, if we put in our lambda average and delta lambda, it works out to be about 2.3 times 10 to the 13th hertz. All right. So in that case, so for the Gaussian, the corresponding coherence time that we would have in that case is, or coherence length is tau sub c times c, and that's going to be 24 microns. For the Lorentzian, we have a L sub c, which is 11.5 microns, and for the rectangular, the L sub c is the greatest, 36.1 microns. Again, so that 20 nanometers might be, an LED source that you have, and so this is the kind of coherence lengths that you have. So if you were trying to make a hologram with a source like that, you'd have to get your two path lengths matched within, roughly 10 to 36 or so microns. Okay, so it's a little difficult to do that, and so that's why the use of lasers is so good for our purposes for making holograms. So let's look at the coherence characteristics of a laser. All right, and we'll look at the type of laser, for instance, that we're using in the lab. So first off, all right, so if we have a typical laser, we might have it's not really a delta function, but we know it's a pretty narrow spectrum, right? So we have, say, nu sub 0 and the full width half maximum, delta nu that we have, it's about 100,000 hertz, 10 to the 5th hertz, all right? So let's say if this were a Gaussian, we just calculated that the L coherence is about, or the coherence, the coherence time is equal to 0.644 over delta nu, and the coherence length, L sub c, c tau sub c, so if we put it 100,000 there, this actually works out to about 2 kilometers. So no problems if we're trying to, we don't, so we've gone from, 11 microns to 2 kilometers. So that's pretty good, except for one thing. Most lasers that you get, unless they're very specialized and in their fabrication and stabilized, oscillate in more than one mode, all right? So what happens when we have more than one mode, all right? So if we have a laser, like for instance, we'll consider something like our Heaney laser that you guys are using in the lab, the red Heaney laser. We can characterize the laser in terms of a gain function. So we have some gas like the neon in the gas, like neon sign. They used to have neon signs, now they're LEDs, but in some of the old bars, you'll still see some neon signs. And the red ones were made with neon, much like the helium neon laser. So we have a spectrum for the emission, which is, again, Gaussian broadened, Doppler broadened. And if the oscillations are made to exceed a loss, which sort of are the threshold losses for the lasing operation. So we have some kind of threshold level of loss that we have to exceed. And when we make the laser, we place this gain medium between two mirrors. And there are oscillations here. The mirrors serve as a resonator to give feedback, have the light pass through that gain medium. So that might be like a tube of your gas. And what you end up getting are, you have certain modes that can oscillate in this cavity. So we have the laser cavity has a length L. And these modes that you would get are repetitive, and they are separated by the speed of light over 2 times the cavity length. So you have nu1, nu2, nu3, and nu2 is equal to nu1 plus c over 2L. All right, so they're related in this manner. And this has to do with phase matching. So if you calculate what the round trip time is here, so we have 2L for a round trip time, divide that into C, that ends up giving you the frequency difference for the modes that oscillate in that laser. So these modes are important because they indicate the stable oscillations in that cavity, all right? And those modes are going to show up as lines here in our emission, in our spectrum that comes out of the laser. So I didn't draw this quite the way I wanted, but at any rate, there's these different modes, and of course the emission spectrum sets the maximum value for those modes. So we could have something that looks like this, where these two modes are separated by c over 2L. This is in frequency, like so. And so the output from the laser that comes out here, the output, is going to look like something like this, where we have, in this case, we're going to have essentially two lines here. And I drew it in this way so we have equal magnitudes for those two lines. Now, they're not exactly delta functions, but they're, for our purposes, we can say that they're close to delta functions. Later we'll see what happens due to the fact that they're not delta functions, but for now, the emission is close to a delta function, all right? So we can write, from knowledge of this, we can write that the power spectral density for this two-mode laser, so this is two oscillating mode laser that we have. Phi of nu is equal to, we'll call this I sub n and I sub n plus 1. So we have a magnitude, say, of I sub, which is set by this gain profile that we have here, In times delta of nu minus nu sub n plus I sub n plus 1 delta of nu minus nu of n plus 1. All right? So we've kind of just written this power spectral density. And again, so this assumes, again, that we're close to a delta function for that width. So it's very narrow and so forth. All right, so now remember that we have, so what we want to see is what is the coherence length for this two-mode laser, all right? So we can get it, again, by writing out what our gamma 1, 2 of tau is for this source, all right, for this power spectral density function. And in terms of the power spectral density function, we said that this is equal to the integral from minus infinity to infinity, phi of nu, our PSD, times e to the j 2 pi nu tau, integrated over d nu, and divided by, if this were not normalized, the total power in our power spectral density function, d nu. All right, so again, we'll follow the same prescription that we did before, where we solve for the complex degree of coherence function. And so if we do that integral, we end up with, again, it's kind of simple here since we have these delta functions, which are very nice. So this works out to be 1 over In plus 1 times In, And again, we have basically these shifted frequencies here, and so they end up as a phase term, in times exponential of j 2 pi nu sub n tau plus I sub n plus 1 exponential of j 2 pi nu n plus 1 tau. Now, there's something nice about this, and that is that these frequencies, nu n and nu n plus 1, are related by c over 2L. They're two adjacent modes, right? So we have, again, so we have that nu, right out here, nu sub n plus 1 is equal to nu sub n plus c over 2L. And if we also write these intensities as kind of normalized functions with this total intensity as a sub n equal I sub n over I sub n plus I sub n plus 1, and a sub n plus 1 equals I sub n plus 1 over I n plus I n plus 1. We can write this gamma 1, 2 of tau now as in the following way. So notice these are just separated by a frequency of c over 2L with the same, so if this is nu sub n here, this really has nu sub n plus c over 2L. So we can factor out e to the j 2 pi nu sub n tau, right? So we have e or exponential of j 2 pi nu sub n tau times a sub n plus a sub n plus 1 times exponential of j 2 pi times c over 2L times tau. Okay, so that's our complex degree of coherence function, and we need to work on this a little bit more to come up with a result. But we'll see that, again, the coherence function is going to be related now to the cavity spacing that we have in this laser. All right, and so we'll get to have an estimate actually of the cavity length or the coherence length for your Heine laser in the lab after doing this. Okay, so on Tuesday we'll go over last year's midterm in preparation for the exam next week. So, okay, see you on Tuesday.